Hello everyone. In this video I want to show you an example of a robot here, the RPP robot, a rotary and two prismatics, or you might also call it a cylindrical robot with 3 degrees of freedom. And if you want to find the Jacobian, if you watch my previous video, you see I used the DH-Denevit-Hartenberg method for finding the Jacobian of the robot. But another way is in simple robots, you should be also to find the Jacobian by directly differentiating the position and the absolute angles of the end effector frame with respect to the base frame. If you take the derivative of those 6 parameters with respect to the joint variables, in this case theta 1, d1, and d2, d2 and d3, I'm sorry, which I showed by star, the joint variables. d1 here is a fixed distance. As you can see, I said it's constant. You should also be achieving the same, Jacobian matrix that you do it with DH. So here, that's my goal, is to do it with a DH method, with a direct differentiation method. So here, if I want to get you the position of the end effector, right? So basically x of origin of 3 in 0, y, and z of that. In this case, I can do it with a simple geometry. It does not need very complicated approach. I mean, all you can do is to move this frame 2 up and down, move frame 3 basically radially out and in, and then rotate this frame 1 with respect to 0, and all other frames, of course, with respect to 0 through angle theta 1. So when this theta 1 rotates and it becomes a non-zero value, basically, if you look from the top view, right, if you look at the top view here, what would you see? So here I'm going to show you a top view. So if this is basically your x0 and this is your y0, right? So let's write them down. The base frame, then frame 1 and 2 and 3, all of these frames that are basically having the same angle because there is no rotary joint between them, they will all be rotated with angle theta 1, which is measured from x0 to x1, or in this case x2 or x3. So if I want to show you frame x3, which is my goal, frame x3 is going to be like this. So this is basically the z-axis of it, and then the x-axis of it will be something like this, where this angle here is what is theta 1. So as I said, this is your z3 and this is your x3. Okay, so in this case, this is when, as I said, theta 1 is not equal to what? 0. Good. So here, if I say what is the x of this end effector and y of it and z of it in the base frame, it's not really hard to calculate that because, as you can see, this point is along the z3 axis with an offset of d3, right? So basically it is a point right here. If I want to draw the end effector, it is basically somewhere like this, where this distance from here to here is what? d3. So if I want to specify the values of it in this case, you can see that x of the end effector in frame 0, right? It is what you can see when we say x in frame 0, so we have to look at the projection along this. So we have to project that point along this x-axis. And in this case, you can see that, of course, it is in the opposite of the x3 direction, right? So you have to go along this axis. So that's this distance here. And that is what d3 times basically sine of theta 1 with a negative sign. So it is going to be what? Negative d3 times sine of angle 1. And also if you project it along the y-axis, so you have this offset, which is d3 cosine of theta 1, and this is going to be y of the end effector in base, and you also need z of the end effector in base. And what is that? Well, for that you can just look at this side view here. You see that the z, because this is your z naught axis, the z is this entire offset, which is simply d1 plus d2, right? So it is going to be d1 plus d2. So the position components of the end effector in base, they are all determined based on my joint variables, d1, d2, d3, and theta 1. Again, d1 is constant. Now for Jacobian, we also need to know the absolute angles of the end effector frame in the base frame. So we need theta x of the end effector frame in the base frame, or here, let me use 3 instead. Frame 3 in frame 0, right? I need to know that. I also need to know the theta y of frame 3 in frame 0, absolute angle, and then theta what? Z of 3 in 0. And again, all of these are what? These are absolute angles. Well, in the first view, it might not be easy to see how you go from this frame 0 to this frame 3 that you can see here by a sequence of 3 rotations with respect to the absolute axis, x naught, y naught, and z naught. And one simple thing you can do is find the rotation matrix. The rotation matrix is much easier here, right? So in this case, if you look at here, I can get you easily the rotation matrix of frame 3 in frame 0 by simply projecting the 3 axes of frame 3 on the 3 axes of frame 0. So the first one is basically x3 as described in x naught, y naught, z naught. Clearly you see x3 has a cosine component along x naught, so it's going to be c1. It has a sine component along y naught, and in this case z naught is out of the board, right? So z naught is something like that, and clearly x3 has nothing along that, so that's going to be 0. Then you go to y3. y3, if you look at the y3, right? Let me show you y3 and let me clean up some of these. So y3 is this guy, and it's down regardless of rotation of theta 1. So that's exactly opposite of z naught. That's all it is, opposite of z naught. And so when I talk about y3, it has to be opposite of z naught. So this guy is -1 and those two others are 0. And finally z3, as you remember, it was a negative sign along x, a positive cosine along y, and 0 along z, because again z is out of the board, z naught. So this is my what? Rotation matrix of frame 3 in 0. Now, if I go ahead and say, hey, now this rotation matrix, if I want to form it with what? With basically 3 absolute angles, theta x, theta y, theta z, how would you do that? Well, for that, you need to know the form of the 3 absolute angles, the form of the rotation matrix. So let's go ahead and take a look at that part. So here, this matrix is equivalent to what? This is equivalent to 3 consecutive rotations. First one is by theta x along x, then theta y about y, y naught of course, and then theta z about z naught. And since they are absolute angles, the order will be opposite of the current axis. It's going to be post multiplication. So instead of multiplying the first one, which is x, then y, then z, you have to reverse it. So it's going to be r z with angle theta z, followed by ry, right, multiplied by ry with angle theta y, and multiplied by Rx with angle what? Theta x. And if you define theta x, theta y, theta z as a symbolic parameter and form these three matrices, let's say in MATLAB, use MATLAB symbolic and form the matrix, right? We want to form the matrix of these. This is the form it will take. So it's going to be C of theta y times C of theta z, and then C of theta z times S theta x, S theta y. Okay, let me go ahead and write the whole thing, stop the video, and then I'll come back. So symbolically, this is going to be this guy that you can see, right? Now, what do we say? We say these two matrices are equivalent, and so we want to find theta x, theta y, and theta z. Well, how do we do that? Well, you can see that here, if I square this one and square this one and add them together, what would I get? Because they both have a c theta y, but they have s theta x and c theta x, so when you square add them together, it's simply going to be c theta y squared, because some of these two other terms squared, s theta x squared plus c theta x squared equals 1. So it's simply going to be c theta y, and now take a square root of that is simply c theta y. And this is negative s theta y. So I can say that theta y is going to be what? Is going to be arctangent 2 of what? Basically negative of this element. And what is that element? That is this guy here. So it's going to be negative of that 0. And then what? And then it is going to be the square root of these two other elements squared added together. So I have to square these two, add them together, and take a square root. So it's going to be what? Arctangent 2 of 0 and 1, right? That's what it is, and of course it is going to be 0. Then what? Then I go to theta x. What is theta x? Well, if you look theta x, of course, you can look at these two elements here that I highlighted. They are as s theta x and c theta x, they are both multiplied by c theta y, which in this case is simply 1. So if I pass this one first and then that one, s theta x and c theta x, to arctangent 2, that's all it takes. So here I need to pass this element first, which is negative 1, and then this guy, which is 0, and that should be what? That should be theta x. And what angle has a sine of negative 1 and a cosine of 0? Well, that's negative 90 degrees. And finally, theta z here, this time I look at these ones, this one and this one. You see, again, they are both multiplied by c theta 1, which is 1. So it's s theta z and c theta z. So if I pass this one first, and then this guy, that should give me theta z. So in this case, it's arctangent 2 of s1 and c1. And of course, that's the same as theta 1. So these are my angles. Theta z is theta 1, theta x is negative 90, theta y is 0. Will that do the work? Yes. If you look here, if I rotate about the x-axis, right, about this guy, I rotate negative 90 degrees, right? So that's positive direction. Since it's negative, so I should go in this direction and go 90 degrees. If I do that, what will happen to frame 0? Well, x is going to stay like that, but y is going to go down and z is going to go this way. So this is going to be z of the intermediate, this is going to be y of the intermediate, this is going to be x of the intermediate, right? Then what? That was theta x. Theta y is 0, so you don't need to rotate about y. And when I say y here, these are absolute y. So now I have to rotate that about this one, 0, which means no effect. And then I rotate about theta z, this one, the original theta z, about this one, I need to rotate by theta 1. Okay, so about that, I rotate by theta 1, and that brings the z here, and it brings the x here, and the y stays like that. So this is going to be y final, this is going to be x final, and this is going to be z final, and that is exactly what you can see here. z3, x3, and y3, which was in the board in this case. You remember y3 here is in the board, right? You can see that over there too. So you see that, yes, these three are really working. These are my angles. So now that they are my angles, I now found them, I'm going to write them right up here, okay? I'm going to say, hey, I found my absolute angles. What are they? Let's write them down. So my angles are negative 90 degrees, 0, and what? Theta 1. Okay, now that I have these, it's time to take the direct differentiation and to find the Jacobian, because I got all that I need. So here, I'm going to copy these, okay, and go down there, and then what? Let's get my Jacobian matrix. So here we go. These are the important information that I needed. Found all of the 6 degrees of freedom of the end effector in terms of the joint angles or constants. And now I'm going to form the Jacobian. So what is Jacobian here? Jacobian is going to be a 6 by 3. And in the first column, all of these 6 degrees of freedom, you take derivative of them with respect to the first joint angle, which is theta 1. So like your top element becomes what? It is going to become derivative of basically x of the end effector in base, that with respect to theta 1. The next one is what? Derivative of y of the end effector in base, again with respect to what? Theta 1. And you keep going down and add all these other ones. So this is what? This is my first column. All derivatives of all of these degrees of freedom with respect to the first joint angle. These are my first column. And then everything is repeated in the second column and third column, but instead the derivatives are going to be with respect to these other joint variables, d2 and d3 basically, okay? So let me write them as well. There we go. So, and I just want to make sure that you're not confused about this d of d, okay? This d is derivative, this d2 and d3 are joint variables. If you don't like this notation, you can call them q2 and q3 and call theta 1 q1, okay? It's totally fine. So we need to calculate these derivatives, and that should not be a hard job, especially with the simple functions we have. So here, if I take derivative of the 6 degrees of freedom with respect to theta 1, well, derivative of this term with respect to theta 1, d3 here has nothing to do with theta 1. S1 is going to be C1, so it is going to be negative d3 times C1. Derivative of d3 C1 with respect to theta 1 is negative d3 S1, right? And this one has no derivative with respect to theta 1, so that's 0. And the theta x and theta 1, again, they are not function of theta 1, so they are 0. And this is with respect to theta 1 is simply 1. Then we go for theta 2, or d2 in this case. The first two have nothing to do. The last three have nothing. This one is a 1. So 2 zeros, a 1, and then 3 zeros, right? So that's what we have. A 0, a 0, a 1, then a 0, and a 0. And then with respect to d3, again, only the first two terms have derivative, and that is negative S1 and C1. Everything else is 0, right? So negative S1 and C1, and then a bunch of zeros. Done. Okay, so this is what? This is the Jacobian of this RPP robot or cylindrical robot. And now if somebody says, for the last part, if somebody says, does this robot have singularity? Well, in this case, remember that although I have 6 degrees of freedom at the end effector, but you can clearly see that 2 of them are literally constant. So 2 of them are not controlled by my joint angles, literally. And you can see them here as well, that I have a bunch of zeros. So these 2 joints play no role in theta x and theta y. Theta x and y are constant, or their velocities, theta dot x and theta dot y, are always 0. And if you look at the other 4 degrees of freedom, you see that they are not all independent, right? So, for instance, if you have x dot and y dot, then the only 2 parameters in x dot and y dot involved are d3 and theta 1. Or in their velocities are d3 dot and omega 1, right? Or theta 1 dot. So if I set my x dot and y dot, that means the values of omega 1 and d3 dot are already taken care of. And if I set my z dot, then that means the d2 dot is also taken care of. So the theta z dot, which is omega 1, is automatically going to be determined from these 2. So I don't have 4 independent velocities, and I cannot have, because my robot has only 3 degrees of freedom. So really, out of these 4, especially the first 2 and this last one, only 2 of them I can select, right? And the z dot independently. So here, really, I don't need this entire J matrix. If I want to talk about singularity, I only need to focus on 3 rows. These 2 are clearly not one of them. And so here, this row is absolutely one of them. It has to be there because I need it for D2 dot. And then between first row, third row, and the last row, I only need to select 3 of them, 2 of them out of the 3. And so it's very common that we go for these 2. So then we only look at this top 3 by 3 portion of your Jacobian. And if you look at there, and set the determinant of this part equal to 0, the determinant of that, if you use the Sarus's rule, you'll see it is going to be basically, if you go here, that's 0. This one is going to be d3s1 squared. And this guy is going to be negative 1 times c1 times negative d3c1 squared. So it's simply going to be d3c1 squared. And if you factor it out, it's simply going to be d3. And this guy should not be equal to 0. So if d3 is 0, that's your singularity. And d3 of 0 means what? Means that if I go back to the robot, if d3 is 0, means basically this point here will come right on the top of the origin of frame 0. And in this case, if I want my robot to be there, all I need is to set up d2 to a specific distance, set d3 to 0. But for theta 1, I can have infinitely many solutions. The rotation does not matter because it's right above it. And if you remember, one of the characteristics of singularity is your inverse kinematics has infinitely many solutions, and you see here theta 1 could be any angle. D2 and D3 are uniquely determined. Theta 1 can have so many angles, so that's indeed a real singularity for this robot. Okay, so hopefully this video was useful to you and you learned how to get the Jacobian through direct differentiation. Of course, we have to determine all of this. And you see for these guys, I used geometry. For these guys, I used basically inverse orientation problem. And then with all these derivatives, I can find Jacobian. So you see here, the difficulty of that is probably the same level as DH. And as the robot gets more and more complicated, in general, this direct differentiation becomes more complex, and it can surpass in difficulty the DH method. So that's why I typically use DH method, but this is an alternative approach. So thank you so much for your attention. I'll see you in the next video.